So the proof we have here today is the nested interval property. And this is one of the direct consequences of the axiom of completeness. So the proof goes like this. For each n-th natural number, assume we are given a closed interval in that goes from an to bn. Assume also that each in contains in plus 1. Then the resulting nested sequence of closed intervals has a non-empty intersection. So what's happening here visually is that we have a infinitely nested closed intervals. We'll call this I1, I2, I3, and I4. And each of the endpoints are denoted as A1, A2, A3, A4, and so on. And each of the right endpoints are B1, B2, B3, B4, and so on. And this nested interval is gonna keep going infinitely. So we are claiming that there's at least one element within the intersection of all of these closed intervals. So the proof goes like this. Assume that the nested interval is constructed as claimed. Let's consider the set A that contains all the left endpoints of the intervals. So A will contain A1, A2, A3, A4, and so on and so on. We know that each Bn serves as an upper bound for the set A. And this is true. If you look at the visualization, we see that no matter which Bn you pick, whatever right endpoint you pick, it is always going to be greater than or equal to all of the left endpoints by the construction of our interval. So that tells us that our set A is bounded and non-empty. And by the axiom of completeness, we are justified to say that X is the supremum of A. Well, X being an upper bound of A means that X is greater than or equal to AN for all n and n. And since each Bn serves as an upper bound for A and X is the least upper bound, by the definition of least upper bound, X is less than or equal to Bn for all n and n. Putting this together, we have X between AN and Bn for each n in the natural numbers. So that actually finishes the proof. The infinite intersection of In, we know that the supremum is contained in the infinite intersection. Thus, the infinite intersection of the closed interval is not empty.